now that we know what a capacitor is, we'll have a look at how energy can be stored on a capacitor. And in order to do that, we're going to refer back to subtopic 5.1, and hopefully you can recall from there, if we're dealing with moving a charge through a potential difference, we're going to do work on that charge, and the work that we do is given by the quantity of charge Q multiplied by the potential difference that it moves through. Keep in mind that work and energy are equivalent, so this value here means that the W we're dealing with is the work that you would do on the charge. It's also then the amount of charge at the end the amount of energy that the charge has gained when you have done that work on it. Now, if we were to represent that graphically, we would consider it to be something like this. That if we were to look instead, so relating it to a capacitor, if we look at the charge that can be stored given the potential difference between the plates, we would find that the line that we would draw there would be directly proportional passing through the origin. The reason for that, we saw that the equation for capacitance was C equals Q on V, and so we could then say that Q is equal to C multiplied by V. Now, we've come across this idea in a few different ways. If we want to look at now, that concept being the area under the curve. So the area under the curve of a Q versus V graph is actually going to be the amount of work that's done. So it's the work done separating the charge, and as I said before, if we're doing work to separate the charge, it means that it's going to be the amount of energy that the charge has now, or the amount of potential energy. So it's the potential energy that the charge has now gained. And in saying that it's potential energy that the charge has gained, it's then hence energy stored in the capacitor. Now, the area that we're dealing with here then, let's imagine that we're looking at this particular potential difference. So the area that we're dealing with is this area here, and so as we said, that's going to be the energy stored in the capacitor. So using geometry here, we can see that the energy is going to be the area of a triangle. So energy here is going to be half times the base, so half V multiplied by Q. But we know that Q is equal to CV from our equation up here, where C would be the gradient of this line. And so instead of writing equals half V times Q, we can write that it's a half V multiplied by CV. So that then gives us the equation for the energy stored in a capacitor as being a half CV squared. So we don't need to know anything about the amount of charge that's being stored. All we need to know is the capacitance of the capacitor that we're dealing with and the potential difference, or the EMF that is being connected across the capacitor, and then we can figure out how much energy is going to be stored in the capacitor. The reason why that's important is that if we're then looking at using that energy, we need to know how quickly it's going to be used, and therefore we can figure out how long the charge that's stored in the capacitor will last and how much energy it can provide for the duration of the time that the current can flow. So that's a fairly quick video. The next video we'll start looking in a bit more detail at capacitance and the physical properties that determine the size of a capacitance.